trajectory, its charge changes, its voltage changes. Since it spends most of its time in the outer solar system, the voltage that it has reflects the voltage in the outer solar system. But as it hurtles towards the Sun, as it enters towards the Earth's orbit, the voltage is changing rapidly, and the comet has to respond to that by beginning to discharge. And that's where we see the familiar cometary phenomena of the coma and the various tails that it produces. This creates a very distinct difference between the two models, the standard model of a comet, which is supposed to be dust and ice left over from the formation of the solar system, and the electrical model, which says that a comet is an electrical body which begins to discharge as it enters the inner solar system. Ever since we've begun to look at comets in close-up, and Halley was the first one that was observed by several spacecraft close-up, it was found to astronomers' surprise that the material coming off the comet was coming in discrete jets and seemed to be coming from what looked like circular areas on the crater. But the imagery wasn't sufficiently sharp to be able to tell exactly what was going on. This required the standard model to come up with an idea that maybe the surface of the comet is coated in black tarry substance or something which was preventing the material from just evaporating from the surface and forming jets as it burst through the surface. But when later images were looked at as we passed other comets, it was found, to astronomers' amazement, that they were seeing very sharp relief. It wasn't like a melted ice cream, it was looking like a piece of heavily cratered rock. Now this fits the electric model of the electrical discharge birth of such a body. In other words, there's very little distinction between an asteroid and a comet other than its orbit. It was in this context that I looked at Comet Tempel 1, which was chosen as the target for an impact. And the idea was that the impact would create a small crater which could then be photographed by the passing spacecraft, and we could determine whether the material was ice or dust or rock based on the size of the impact crater. It seemed to me that if this comet was a charged body, there would be several other effects that were unexpected. Principally, as a metal copper object approached the comet, there should be an electric discharge to that copper projectile. In other words, there would be an initial flash, and then there would be the impact itself. And the impact, I suggested, would be far more energetic than was expected, because it would tend to concentrate the electrical discharge in the area of the impact, and also it may change the nature of the jets nearby. So it was with great interest I awaited the results of the impact and watched it on television. Before the impact, the astronomers in the assembled control room were worried that they wouldn't see anything, that the impact would result in a very small puff of dust, and that would be the end of it. So when the impact occurred, they were surprised by two things. One was that there was an initial flash followed by the main impact, which was so energetic that some of the sensors were almost swamped, and the passing spacecraft was unable to achieve its primary aim, which was to photograph the crater. A part of the surprising brightness of the dust released from the impact with Comet Tempel 1 was due to the fact that it was so intense and so widespread. And one of the initial findings was that it seems to be very finely divided dust. Now this is the same thing that was found at Comet Halley, and it was a surprise then, so it's rather surprising that they are surprised once more. The point is that an electrical discharge on the surface will release material, dusty material, very finely divided. It's a technique that's used in sputtering of metals onto, for instance, astronomical mirrors. So this production of very fine dust is to be expected in the electrical model. But in the standard model, you are asking ices to evaporate or to sublimate, and in doing so to drive off pre-existing dust grains. So there's no way that the dust can be finely divided. It will be in its pristine state. So the production of this great cloud of very fine dust is rather inexplicable in the standard model. The electrical model of comets was driven for several people by Velikovsky's challenge that the solar system had electromagnetic forces to be taken into account. And one of the early pioneers in addressing this issue of are comets an electrical phenomenon was Ralph Jurgens. When he proposed the electrical model of the Sun, it implied that all bodies in the solar system must have, to some degree, a cometary appearance or a cometary effect associated with them. Ralph Jurgens, in his model of the Sun, showed that bodies moving radially towards or away from the Sun would experience electrical forces which could induce a cometary display, that is, a visible display. Also working in later years with Ralph Jurgens was Dr. Earl Milton, and he made some predictions and statements about the impact of Comet Shoemaker-Levy 9 fragments with Jupiter. And his view of the electrical nature of those impacts was also vindicated. In the electrical model of the solar system, any body moving away from or towards the Sun at any great rate, for example like a comet, will experience electrical effects which result in a cometary appearance, and that could apply to a planet. Now Velikovsky, in his research, found that Venus was described as a stupendous comet at some point in ancient times. So it was very gratifying for him to be able to announce at the conference in 1974 that astronomers had discovered what they called a cometary tail of Venus. Some years later, it was announced that it was discovered that stringy things were coming from Venus. And of course, this was confirmation to the electrical model because plasma currents flow in strings. This discovery of a cometary aspect of Venus raises the issue of the intense heat we find on Venus. That intense heat is not well explained at all by any idea that the planet is somehow a twin of the Earth's. It raises the distinct possibility that Venus has had a far more dynamic history than we've been taught.
Our ancient ancestors were obsessed with the comet. Let the slightest wisp of a comet appear in the sky and all of humanity was thrown into terror. But why was this? It was cosmic catastrophe that inspired the ancient words and phrases for the comet. The comet was the torch of the sky, the sword hanging over the world, the spiraling serpent or dragon, the spiraling sidelock or ribbon. The angry or lamenting goddess soaring across the sky, her hair disordered and blowing in the wind. Anyone exploring the roots of the ancient comet fears is going to run into the work of Immanuel Velikovsky, the controversial theorist who suggested that, well, there's a reason for the fears of comets around the world. We experienced this horrific cometary catastrophe. The world was devastated by a comet just a few thousand years ago. And Velikovsky went further. He said that not that long ago, planets appeared in the sky with comet-like attributes. In particular, he named the planet Venus as the great comet of antiquity. Both Walt Thornhill and I disagreed with many components of Velikovsky's reconstruction, but we also felt that Velikovsky had nailed certain principles that can help us to understand the early cultures. In particular, Velikovsky was correct in naming the planet Venus as the Great Comet. And the cometary language of Venus goes far beyond anything that Velikovsky himself published. In every corner of the world, the language of the comet and the language of Venus are identical. Venus as serpent or dragon. Venus as torch of the sky. Venus as long-haired star. Venus as bearded star. The Sumerian goddess Inanna was identified as Venus. She was the Lady of Life. But in her terrible aspect, she became a dragon-like flame in the sky. The texts say, like a dragon, you have deposited venom on the land, raining the fanned fire down upon the nation. Inanna became a roaring storm. She devastated the land. Mankind comes before you in fear and trembling at your tempestuous radiance, the texts say. Inanna's Babylonian counterpart Ishtar was also identified as Venus. She was the shining torch of heaven and earth. Furious and irresistible onslaught. I rain down like flames, the goddess announces. The Egyptian goddess Sekhmet has the same attributes. She takes the form of the fiery Uraeus serpent. She becomes a flame of fire in her tempest, a star scattering its flame and fire. Sekhmet herself says, "The fear of me is in their hearts, and the awe of me is in their hearts. No one at all can approach her," the coffin texts say. The streams behind her are flames of fire. The astonishing fact is that goddesses everywhere exhibit this terrifying and cometary aspect. The Canaanite Inat, the Hindu Kali and Durga, the Greek Aphrodite, Athena, Medusa, and countless others. And of course you can add numerous counterparts in the New World, from the Incan goddess Chaska to the Aztec goddess Xochiquetzal to the legendary Nokomis of North American Indian tribes. The serpent or dragon is an unexplained mythical archetype. There's nothing like it anywhere in the biological world. And yet the same recurring features will be found in cultures the world over. The dragon's disheveled hair and shaggy beard. Its knotted aspect, and its worldwide appearance as entwined twins. Its fiery or lightning-like emanations, and its effusive feathers. In all of the ancient serpent or dragon images, it's the luminous, filamentary, braided, spiraling, metamorphosing, and destructive aspects that stand out. The very traits of high-energy plasma discharge. The attributes of these mythic monsters remain unexplained only until we see the hairy and feathery attributes of the electric arc in the laboratory. We see precisely the same thing in enhanced images of the comet's tail. And we we see the same thing in the comet-like discharges of distant nebulas. Gases in a vacuum